Hello, welcome back. We're going to continue with our lectures on Markov processes, and we're now introducing Markov chains. This is going to be a three-lecture series. It's based on chapter 2 of the Dubrow book, and in this three lectures, I'm going to establish the basics of Markov chains. In short, Markov chains is probability meets linear algebra, and they're very fun random processes. Think of ODEs, PDEs, but with some randomness attached to it. And what we're going to discuss is a certain set of dynamics that allows you to do computations through linear algebra. So, and they cover a wide number of examples, and they have lots of application in the real world. So these are very interesting objects. And the way that I want to go through this topic, this introduction of to Markov chains, is through three lectures. In the first lecture, I'm gonna work on a motivating example, a random walk, and this motivating example kind of is what sets up the theory and what kind of informs the properties that we want for our random processes, our stochastic processes. But it's a little bit too general and or too theoretic heavy, for instance, or we need to work on something simpler first before we move to considering this random walks that I will discuss today. But I want to use it more as a motivation, as something that we're trying to understand, and we're gonna dial it back and try to understand something slightly simpler. In particular, the random walks, what's happening is there's there's some infinity there. Our state space, which I'll describe later, is infinite. But in this introduction to Markov chains, we're just going to consider finite state space. And in those cases, the theory is more well behaved. And but nonetheless, I think random walk is a very intuitive, motivating example. And I think what we want to do is that we eventually want to be able to understand that. And this will be a motivation that will also work for the following chapter, chapter 3, and the following series of lectures. But once we've established this motivating example and we introduce some computations, we are going to move on to the next lecture where we're going to do the simplest example of a Markov chain. And we're going to focus on something very specific and very concrete and just try to understand the theory in that case, in the simple case. And the simplest non-trivial case, I should always say, because the trivial case is the most trivial case is too trivial. But the simplest non-trivial case is n equals 2, and in that case, we can start setting up the theory. And here n is the size of the state space, which I will describe in lecture 8, I believe. Yeah, in the following lecture. And once we've gone from the motivating hard problem then to the simplest non-trivial problem, in the last lecture we're going to set up the general theory for a finite state space Markov chain. And throughout this, our focus is in computations. We're going to have a random process, and we want to figure out the probability of certain events. And with this in mind, this is what's motivating all of this theory that we actually want to do computations. And the punchline at the end of the day is that all these computations are going to follow by linear algebra. And this is what we're slowly going to get at. But throughout this whole process, I'm going to do it through posing questions, trying to get us to the right answer by some motivating questions. So the general picture will be in lecture 9, and in the first two lectures, I'm motivating through a very specific example, and then through a very simple example, and then in the last lecture, we'll get to the sweet spot. So here, the motivating example is a random walk. We'll get to the details later, but the first, what I want to establish is a picture. And here, my random walk is going to be this random variable st. And t really denotes time. And it's in here we have the trajectory of a random walk. So it moves up, down, up, down, up, down, up, down, up, down, up, down, up, down. And it arrives at some location x over here at time t. So s of t is going to be a random variable, which depending on its trajectory, it could be somewhere else. So there's some randomness, and it's not deterministic, but it's some random process. It's some evolution of a random variable depending on some time. And the basic question that we want to answer for a random process like this is what's the probability of finding your random walk at time t in location x. So this is the very rough idea of what we want to compute. And we'll get to it. But first, I want to actually upgrade this question. I want to think of something more general. And not only do we want to know the location of the random walk at time t, we want to know more. We want to know the location at different moments in time, t2 and t1. And we want to find out what's the probability of this event, that you have a random walk that goes through this position, and ends in this position. So the probability that all these three events happen. And here, this is one specific sample trajectory where this happens. And the rough idea is that each trajectory has a certain weight to it, and we need to figure out the weight of all the trajectories that goes through this point. So this is one specific sample. We could have had another sample where it went through here, and then it goes through here, and then it's up to here. So we need to find it all the, well, we're not really gonna find all the trajectories, but in theory, what we need to do to compute the probability is find all the trajectories that go through these 3 points and sum all the probability weights. Now, coming up with all the trajectories that go through all these points is actually a combinatorial nightmare. So what we're doing here is we're developing tools to compute these probabilities without trying to figure out all the paths and trying to set up a systematic method to do this. And we'll start working on this problem and try to motivate our computations. So the main idea to compute this probability is to use conditional probability. So we start on the left-hand side, the probability that we go through these 3 points in space and time. We use conditional probability. In here, the first thing is to multiply and divide by this quantity. So this is just a manipulation of our probability function, which if this is a non-zero probability, then if this is a non-zero probability, this is fair game. If this is a zero probability, then this is a zero probability, and we don't really have anything to compute. So we're just safely assuming that this isn't going to be non-zero. And then by the definition of conditional probability, we have that the probability that this is going to be the conditional probability, condition this event, times this probability. So what the idea here is to use conditional probability to compute this probability. And in here we're asking about the probability that the random walk is at position x, given that it has gone through positions x2 and x1 as time t2 and t1. And then we multiply it times the probability of that event happening. And we can do the same procedure that we did here of multiplying, dividing by this quantity, and using the definition of conditional probability to rewrite this probability as a conditional probability of the probability that you go through position x2 at time 2, given that you go through position x1 at time t1, and then you multiply it times the probability that you go through position x1 at time t1. Gotta clear my throat. Chug some coffee. All right. So this is the idea. You might argue that we're nowhere closer with after this computation. At this point, you'd be right that we're nowhere closer, but the point of what's going to happen next is that we're going to be able to simplify this conditional probability. And you might try to guess how, and we'll develop this and we'll give certain circumstances under which this conditional probability is maybe simplified. And these are natural, and this not the circumstances are natural, and they should be they're not crazy or out of the question. And I'm trying to motivate that this will be the case. But the way that I want to do this is through actually looking more at the dynamics or the mechanism of a random walk and try to see how to simplify that conditional probability through an intuitive understanding of the dynamics. So I have, and I haven't described the mechanics at this point. So that's why up to now, this equation and this equation are equivalent. And because we really don't have any knowledge on the dynamics, we really need to understand the dynamics more to simplify this. And I purposely left that out to talk about it till now so that we can think about it more carefully through the lens of the conditional probability. So let's look at our random walker. Here we're at a precise location in time, at time t, and we have that at time t our random walker is at location x, and after time t it's moving in the lattice, in the integers. It's either going to jump to the right and jump to the left. And the way that I'm doing the dynamics in particular is that at time t the random walker is going to flip a coin, and it's going to move according to that coin. If it's heads with probability p, it's going to jump to the right. If it's tails with probability q, it's going to jump to the left. And here I'm taking the simplest non-trivial dynamics, and I'm having the particle just jump to adjacent locations. Potentially, you can, instead of doing a coin, you can do an n-sided die, and you can have longer range jumps and shorter, or that you can go back to the same position. You can add more complicated dynamics, but for now, this dynamic suffice. And I think this dynamics are natural, and at each moment in time, we're making a random choice, and we're determining this choice by a coin flip, heads or tail. And it's going to be a biased coin flip, or it doesn't have to be a symmetric coin flip. P and Q don't have to equal to 1, but you either have to move to a left or right, so that we have a P plus Q is equal to 1. And since this is a probability, they're going to be greater than or equal to 0. So this is my picture for the dynamics of a random walker. So it's going to move to the left or right. And in particular, if I want to write this into a formula, I say that the position at time t plus 1 is equal to the position at time t plus k. And k really represents my coin flip, and it's determined it's either going to be plus or minus 1. It's going to be 1 if it's heads, or minus 1 if it's tails. So this k really represents our coin flip. And we see that it's going to move up plus 1 if it lands heads, P, minus 1 if it lands tails, and otherwise it's going to be 0. So this are going to be the dynamics of my coin flip. Let's start of my random walk. And moreover, we need an additional independence condition. So again, these are my dynamics that I decide to move left or right based on a coin flip. And additionally, I'm going to have that my coin flips are independent of each other. So if I flip my coin at time t, the outcome of the teeth coin flip is not going to affect the outcome of the t+1 coin flip. And this is an intrinsic property of coin flips. They're memoryless. They don't know what happened. They're independent of what happened in the past, and it's with the same probability. It's going to be heads or tails. So this is going to be independent coin flips. And in particular, this is a place where you can start making things a little bit more sophisticated. Potentially, you could make the bias of the coin depend on time. But throughout this whole series of lectures, we're going to assume that the coins that we're working with is just the same coin with the same bias, and we're not switching from one bias coin to the other bias coin with different biases. So we're just going to be flipping the same coin. It's just going to be an independent outcome each time. So there's no dependence on the biases or the rates or the probabilities of the coin flip over time. And so this is going to be our key feature for conditional probability. If you recall the definition of conditional probability or working with conditional probabilities, recall that conditional probabilities always simplify with some independence condition. And this is the independence condition that's going to simplify our computations. And in particular, to say it more formally or explicitly, what we have is that the increments of our random walk are going to be independent. So the increment from time t to time t+1 is going to be given by this difference of xt. Actually, I believe I've switched notations. Yeah, so I'm denoting my random walk by s. So this should be s. Quick fix. The increment of my random walks from time t+1 to t is going to be given by this difference of the positions. And so the first increment is this one, the second increment is this one, and the third increment is this one. And they really are just, if you go back to this formula, if you look at the difference of this and this, it's really just equal to k, which is plus or minus 1. These are really the teeth coin flip, the outcome of the teeth coin flip. And they're going to be independent random variables. So if you look at this, all these random variables at this difference of the positions, these are going to be independent random variables. And this is the independent condition that we have. And it really just means that every time we flip a coin, we have an independent outcome. And this is what's going to simplify our computations. So now what we want to reconsider is this probability of finding our random walk in these positions at the given time. So position x1 at time 1, position x2 at time t2, and position x at time t. And this is, just to bring it back, this is the picture that we have in mind. The probability of an event like this, where we have fixed this, this, and this. And what we did before is that we rewrote this probability as a product of conditional probabilities. And what we claim now is that we can simplify this conditional probability using independence. And this actually goes through the name of the Markov property. And in here, what the claim is precisely is that the probability that you're at position x at time t, given that you're position x2 at time t2, and x1 at t1 is just going to be equal to the probability, the conditional probability that you're at position x at time t, given that you're at position x2 at time t2. And recall for what we've done so far that t2 is greater than t1. And this is important because the statement doesn't hold other way around. So it really, in this Markov property, which I'll define more precisely in the next lecture, and this is a specific version of the Markov property. In this case, it's important that t2 is greater than t1. the smaller time is the one that gets crossed out. And in particular, so looking at this Markov property, if we try to digest what it's really telling us, is that the probability that this probability condition on these two events is independent of the earlier event. So in here, where was T1? So T1 is right here. This is T1. And this is saying that this probability is independent of what happened at time T1. It only depends on what happened here at T2. So if we condition on if we condition that it's here, then the probability, if we condition on a path like this, that goes through T1 here and T2 here, or if we condition the probability that of the path ending here, given this and this, it's going to be equal to the probability of the path ending here, given this and this. And in here, the important part is that it goes through this point, and then what happens earlier in time doesn't matter. So if it first goes through all this, it's not going to influence the probability from this point forward. So what this statement is telling us is that if we're conditioning on this event here, the probability of what's happening moving forward is independent of any event happening here. So this is going to be the Markov property. And this really follows from the coin flipping analogy, the coin flipping dynamics, the memorylessness. So in here, you could have had a lot of tails and then a lot of heads, and this is not going to affect the probability moving forward. Or you could have just stayed on average, and then the probability is not going to be affected moving forward, because the coin doesn't remember that it's been doing great or it's been doing bad. It just looks forward. Great analogy in life. It's very zen. This coin doesn't think about past failures or successes. It just moves forward indifferently. So this is the Markov property, and this is going to be a key property of this Markov chains or Markov processes that we're studying, that the dynamics only depend on your current position. So if you know that you're here and you want to move forward, the dynamics only depend on the fact that you're here, and they're independent of whatever happened before. So this is going to be the key property for Markov chains, that your dynamics moving forward only depend on your current state. And they do depend on your current state. We can't remove this position, because if we stay with the coin flipping dynamics, if we're here and we want to end here, then if we have a fair coin, that's not unlikely. But say we condition on somewhere right here, then going down here using a fair coin, it's in fact impossible, because we only move down by one each coin flip. So the probability of going from somewhere really high up down is going to be 0, but if you go from somewhere here, it's going to be non-zero. So moreover, we have that the best that we can do is have this conditioning on this one. We can't remove all the conditions in the conditional probability, but we can remove all but one. And the one that we can't remove is the last one, the one that's most recent condition. And then anything in the past doesn't affect our conditional probability. And this is called Markov property, and I give a definition in the next lecture, the more precise, and it's going to be the foundation of our Markov processes. This is the theoretical foundation, and in the next few lectures, we're going to adapt this property and use it for computations. And we'll see that given this property, we can then use linear algebra to compute different probabilities. So let's look at the proof. And after the proof, I believe we'll finish lecture. And that's a drink of water. For some reason, my throat is dry. All right, so let's look at this proof. Again, we're trying to prove this identity. And what I'm going to do is compute this right-hand side and obtain a result, and then compute this left-hand side and obtain the same result. So I'm going to compute both sides of the equation and show that they are equal to the same quantity. I start with the right-hand side. It's the most straightforward. The computation is essentially the same for both sides. So this one is, I believe, easier to follow. So probability that you're at location X at time t, given that you're at location X2 at time t2, by definition is given as this ratio of probabilities. And here, this is the key manipulation in this proof and the key insight, and this is where we'll be able to use independent increments. We note that this event, that ST is at X and the random walk is at X2 given time T2, is equal to these two conditions, that the random walk is at it's at X2 at time T2, and the difference of this, ST minus ST2, is equal to X minus X2. So you can check that these two system of equations are equivalent. So if this system of equation is true, then it implies this one, and if this system of equation is true, then it implies this one. So using this observation, we just rewrite this event as this event. And now we use the independent increment condition. So the increments from time t2 to t are going to be given by this quantity, and this is going to be the increment from time 0 if we start at origin to time t2. So these two increments are going to be independent. So we can take the product of the probabilities. And now we see that we can simplify. We can cancel this and this, and we see that the probability that you're at location X at time t, given that you're location 2, X2 at time t2, is given by this probability, that the probability that your increment is equal to X minus X2. So we obtain this simplification for this conditional probability, and we'll simplify the left-hand side similarly. So again, we start with the conditional probability, and we re-express it using the definition as the ratio of two probabilities. And we manipulate the events here. And again, we write them as increments. This is the increment from time 0, given that you start at the origin. This is the next increment, and this is the next increment. And now you can check that this event here is equivalent to this other one, and the check is similar as in the previous case. And now we can move forward and look and simplify or use the independent increment property to write this as the product of these probabilities. And again, using the independent increment property, we can write this as the product of two probabilities because these are independent increments. So I should have noted that you can also manipulate this event and show that it's equal to this event. And then you can do that this is equal to this using the independent increment property. And you can simplify, canceling this out. And we see that this conditional probability is just equal to a probability that the increment from t2 to t is equal to x minus x2, which is the same thing that we had in the previous case. With the left-hand side, we showed that it's equal to this, and the right-hand side, we showed that it's equal to this. So we have the Markov property. And that's it for lecture 7. So in this lecture 7, I just wanted to give what I believe is a natural example to consider a random walk, where you just decide where to move based on a coin flip, and highlight the memoryless property and how the coin has the memoryless property. This leads to independent increments, and based on this, we can simplify our conditional probabilities. And the way that we simplify our conditional probabilities, this is what we call the Markov property. And this Markov property is going to simplify a lot of computations. And we'll gonna see the implication of this Markov property in the next lecture. Do some specific computations, and we'll work on the simplest example thing. All right, thanks for watching.